This lesson, we will talk about precipitation hardening. Precipitation hardening is also called as edge hardening or particle hardening. It's a type of heat treatment technique that we use to increase the yield strength of a malleable material, including most structural alloy of aluminum, magnesium, nickel, titanium, and some steel and stainless steel. The process does this by produce a uniformly dispersed particle within a metal's grain structure that help to stop the motion of dislocation and as a result will strengthen the metal, uh, particularly if the metal is malleable. What does it mean by malleable? We can say that malleability is a physical property of metals that define their ability to be hammered, press or roll into a thin sheet without breaking. Or in other words, it is the property of metal to deform under compression and take on a new shape. A metal's malleability can be measured by how much pressure or compressive stress it can withstand without breaking. The differences in malleability among different metals are due to the variances in their crystal structure. So we can say that the precipitation hardening is a form of heat treatment that help to increase the strength and hardness of metal. It is a process of strengthening the material by heating the specimen from a 30 minute up to 1 hour, followed by a rapid cooling, or what we call as a quenching, and finally aging at room temperature or at an elevated temperature. And the formation of a hard precipitate will act as a barrier to dislocation motion. And this technique only applicable only to some alloy system, for example, stainless steel. The details of how the precipitation process works can seem a little bit complicated, but a simple way of explaining it is by looking generally at the three steps that are involved. First, we have solution treatment, quenching, and edging. So, in general, there are three steps that are involved in precipitation hardening. First, we have a solution heat treatment. Then we have quenching or rapid cooling. And lastly, we have precipitation heat treatment. And what we will get from precipitation hardening, what we got from precipitation hardening is a harder and a stronger material. So before we discuss precipitation hardening, we have to understand the important role of dislocation in the deformation of materials. In a perfect crystal, we know that the atoms will arrange in a perfect pattern. Dislocation, as we know, aligns of atoms where the perfect pattern of atoms is broken. And one way to harden the materials by adding something that will stop or will block or slow down the movement of dislocation. Uh, Precipitate can do that. Precipitation hardening is the hardening of a material due to the growth of precipitate that will impede the movement of dislocation. The strength and hardness of some metals alloy may be enhanced by formation of extremely small, uniformly dispersed particles of second phase within the original phase matrix, like what we can see in the figure here. And this is can be accomplished by appropriate heat treatment. The process is called precipitation hardening because of small particles of the new phase atom precipitate, as what we can see in the cartoon here, and in the actual picture of precipitate in metal. So there are three steps that involve. First is a solution treatment, quenching, and edging. In solution treatment, the alloy is solution treated between 500 to 548 degrees Celsius. And here, the alloy is first heated above the solver's temperature, and we held it until we get a homogeneous solid solution. And secondly, we quickly cool down the solution, soak metal, and after the solution treatment, the alloy, which contain only in its structure, is rapidly cooled. And after quenching, the solution is a supersaturated solid solution that contains excess copper. That is what we call as a metastable structure. Uh, Supersaturation is a solution that contain more of the dissolved material that could be dissolved by the solvent under a normal condition. And finally, we heat the same metal to a medium. We heat the same metal to medium temperature. Cool it and cool it quickly again. The supersaturated is heated at a temperature below the solver's temperature, and at this what we call as edging temperature, the atoms will diffuse only a short distance, and what we will get is ultra fine, uniformly dispersed second phase precipitate particle. So graphically, this is how we can represent a process that involves in a heat treatment, as shown in the figure here. So in the first step, as shown by the red color here, we have a solution heat treatment where all the solid atoms are dissolved to form a single phase solid solution. Then we have quenching, shown in the yellow color in the figure here, that can be defined as rapid cooling to a room temperature to create the supersaturated solid solution. And finally, we have precipitation heat treatment, as shown here. This is where all the precipitates starts to form a finely dispersed particle, and this process is also known as aging, and is the last and the most time consuming the step of precipitation hardening. The solution is heated to an intermediate temperature. For example, for a stainless steel is between 400 degrees Celsius to 500 degrees Celsius. And here the part is held in a constant heat. The exact aging temperature depends on the composition of the material. The oversaturated solid solution will transform into two-phase alloy, and the dominating phase is also known as a matrix. And here we have some example of application of a precipitation hardening. One of the example of application is internal wing structure on Boeing 767. The aluminum is strengthened with a precipitate that formed by alloying. We can see at the bottom here a transmission electron micrograph showing the microstructure of the aluminum alloy that's used for the upper wing skin, parts of the internal wing structure, and selected areas of the fuselage of a Boeing 767 here. And other than that, we have aluminum alloy 2219, an aged hardenable alloy that is produced with a copper additive. Aluminum alloy 2219 consists of aluminum and 6.3% copper. It is well known for its excellent structural strength and used for many applications, especially in high temperature application. Here we have some requirement for edge hardening. Not all alloys can be edge hardened. Four conditions must be satisfied. for an alloy to have an edge hardening response during heat treatment. The first one is the alloy system must display decreasing solid solubility with a decreasing temperature. Or in other words, we can say that the alloy must form a single phase on heating above the solvers line, then enter two-phase region on cooling. And the second one is the matrix should be relatively soft and ductile, and the precipitate should be hard and brittle. In most edge hardenable alloy, the precipitate is hard, brittle, intermittently compound. And the third one is alloy must be quenchable. Some alloys cannot be cooled rapidly enough to suppress the formation of the precipitate. Quenching may introduce some residual stress that can cause a distortion of the part. And to minimize residual stress, for example, aluminum alloys are quenched in hot water at about 80 degrees Celsius. And finally, a coherent precipitate must form.